Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So, fine, we will start from where we left in the last lecture. So, we were in week 9, we were discussing about this LQR design, which is one of the quadratic program based techniques for controller design. So, fine, I believe we have already set up the objective function here, and we have already observed that this would be a parabolic function with respect to x and u together as the state, right. And hence, what we want to do is we want to figure out the sequence of control inputs which is going to minimize this function. And not only that, we have also observed that we can apply this principle of optimality here. That means, what we will do is we will solve the method by unrolling back from the nth step to the 0th step, because we will assume that the control inputs we are trying to figure out, they will be such that they will be optimal with respect to the state where a decision is taken, okay, so that all the future decisions continue to be optimal like that. So, fine, what we will do is we will try to figure out the last control input, let us say at the n minus 1th step, assuming that all the previous control inputs have already been optimal, and then, like I said, we will unroll back in time. So, let us see how we approach this optimization problem. So, what we will do, so just to recall, if you remember, we have already set up this cost function here, okay, and for this cost function I have a quadratic form over x and u, right, and a summation over that, and finally, the last state also appears as a quadratic term, and here we have all these components of q written down like here, and we have already defined them earlier. So, we have already defined them earlier like this q1, q12 like that, fine. So, most of this treatment has been taken from Angstrom's book on digital controller implementation. So, if you want to study this thing in detail, that would be the reference to go for. Okay. So, fine, let's go ahead with this problem solving right here. So, what we will do is we will first assume some component Sn here. That means, it is some value of a function s at the nth step, okay, and let that be some. So, that is q0, which is kind of let us say that is equal to some parameter wx here. Okay. Now, what we do is we define the minimum value of the loss, something like this. So, let the minimum value of the loss be this for the initial state. So, if you see, we are bringing in many notations. We have defined something called Sn, which is a sequence S1, S2, S3 like that up to Sn, okay. And we are saying that, well, let that be equal to q naught, which is defined earlier, and let that be equal to some wx here, okay. And then we are trying to define this loss function in a different way using this variable v naught. So, basically, we are connecting the value of j with the number of steps we are considering in this loss function, okay. So, let us understand what it means. So, if you recall, what really was j? So, j was something like this summation, right. J was this summation over an nth step, right, where you are trying to figure out all these 0 to n minus 1 control inputs, and finally, that n step value, right. So, what we do is let us consider that function. So, technically j was like expectation of that summation, if we recall. Now, going inside that, let us define something let us try to calculate what is the partial sum starting from the kth step up to the nth step. So, that means we are trying to figure out these control inputs u k plus 1 up to u n minus 1. So, we are just writing the usual function here. So, this was our original function, right. So, just consider we are we are taking it not from 0 to n minus 1, but from some kth step to n minus 1th step. Okay. So, then we start calling it as something like V k, okay. And of course, you have the nth step value. So, this is it, right. So, this is what is, right. So, this is the so, that means, if I say set k to n, then we have V n, right, and V n won't have this summation at all. So, V n would be like this x transpose n, this final weighted value q naught x n, right. Now, we have taken that to be S n right here, right. So, we will have V n as x transpose n S n x n. So, we are using this relation right here. Okay. So, now let us try to do something. Let us mind our objective. We want to figure out what is the last optimal control input, right, assuming all the previous decisions have already been optimal. So, what we need to do is, this is what we have V at the nth step, we want to figure out u n minus 1. So, we need to unroll this thing and create suitable values of x and relate them basically with suitable values of x from the n minus 1th step, right. So, if we just try to do that here, so we continue from here. So, what I am doing is I am replacing x n by its recursive definition in terms of x n minus 1. So, this is what we have here, right. So, now let us try to do something similar and figure out well what is this V n minus 1. So, I hope this is clear, right. I mean, all we have done is we have unrolled these values of x n and written them in terms of x n minus 1. Now, if we try to derive what is V n minus 1, let us understand how it really should be, right. So, V n is just the last prime thing, right. There is nothing as part of the summation part of the original j, but now when I talk about V n minus 1, it will at least have the last part of the summation, right, with the n minus 1th step followed by this expression of V n, that is the last step's value, right. So, if you remember the form of j, right. So, just to recall, you can just look over j was something like this, that was a summation, right. So, we just have V n with this value, right. Now, let us write V n minus 1, V n minus 1 will have one term from here followed by the term for V n, right. So, let us see. So, it will just have the last element of the summation. So, that would mean the quadratic terms of x and u in the n minus 1th steps. And you have the weight for, let us call this as W x, the weight for x like we defined earlier. So, this is the minimization, essentially we are just considering the last step, plus there should be V n, right. I mean, of course, I need to have this inside the minimization, because V n is the last term. So, this is coming as the last term in the summation followed by V n, which is the last term. So, that is what you have, right. Now, let us understand what we want to minimize. We want to minimize the these values of x t and u t squares, right, because we do not want the control to be abrupt and we want the state to steer away too much from the equilibrium which is at 0, right. So, well, let us figure out what we can do. The idea is, since I want to minimize just these square terms, that means excess we want to minimize the terms like these ones, right, because that has been my objective, right. Now, in the process we have these covariance terms clicking in, right. So, what I mean is fine, I hope this is understood. So, we can just delete these parts. So, if you see in our original this was the nice looking thing, right, but if you go back here you have terms like this, right. So, you have terms like this, you have terms like this, these are the ones I want to minimize, and then the covariance terms we have I mean they also appear, right, but what we can do is we can ignore these covariance terms of x and u in our subsequent derivations, and we will consider some distribution, considering that for some distribution the covariance of x and u are 0. So, let us understand what I am just saying. So, this is the loss function. We are saying that well, under some distributions we can assume these covariances between x and u to be 0, right. I mean they are independent, I mean of course that depends, but overall let us understand what I want to do. I want to minimize the terms like x square and the terms like u squares, right. So, that is why I will focus on these terms of the loss function, and I will see that if I minimize them, then also in a way I am minimizing the sum, but one may argue that there exists this covariance, but we will ignore that for this part of the derivation here. So, the way we will ignore is, like I said, that we will assume that these values of x and u, they are following some distribution where this covariance happens to be 0. I mean, there is no covariance relation between x and u. So, fine, let us now proceed over that. So, I just wrote V n minus 1 equal to something plus V n, and we also expanded V n earlier. So, let us put all of them together and write the formula now. So, I am using subscript instead of bracket here for the sake of simplicity, otherwise there would be too many of them. This is the weight parameter for the x's. Okay. So, if you see, we are kind of simplifying the derivation formulations now. So, instead of writing those q1s, q2s, right, we, in order to relate that, well, this is about x, we are just writing the weight wx. Okay. So, similarly wu. Now, if you remember, here we had V n, and previous to that we had expanded V n, right, and our V n expansion, let me just rewrite, it was something like this, right, that phi x n minus 1 plus gamma u n minus 1, right, and that is transposed. Then you have S n, and then again phi x n minus 1 plus gamma u n minus 1, right. So, pretty much that is what it was. So, we need to carry out this multiplication and then write the V n here. So, that is the deal, right. Fine, let us do that. So, this would really mean that, well, this will be transposed, this will be transposed, and then they will get multiplied, right. So, I am just writing this transpose followed by multiplication step right here. So, this will go forward, right. So, x transpose n minus 1 phi will be transposed, then S n will be there, right, and then I have phi, then x n minus 1 plus. So, I am expecting 4 terms out of here, right. So, you will have u transpose n minus 1, gamma transpose S n phi x n minus 1, right, and then again take this, and this term needs to be multiplied now with the other two. So, that is what we get, right. So, fine, we can write this in a modified way, something like this. So, we can actually combine certain terms here. For example, you can I think you can combine, because they are all in the quadratic form of x, right. So, you can combine these two, and similarly you get let us identify the quadratic terms of u. So, you can combine this and this, right. So, let us do that then. Yes. Yeah. So, yeah, but of course, there will be more terms. So, let us not put this bracket here, and instead let us just nicely write down the other terms, right. But the good thing is we have successfully written the quadratic terms over x and u, right. So, fine. Now, let us just consider these terms here, right. The terms relating x and u, right. We have created the ones for quadratic in x and quadratic in u, and here are the other terms. So, we have taken care of this one here, and then the one that is remaining is this one. Yeah. So, that is the 4 terms, right. Now, let us observe something interesting. We are trying to minimize over u, right. Now, if you see the first term, it cannot have any role over that minimization. So, this does not have any u at all, right. So, fine, let us consider the other 3 terms, and let us try to rewrite this minimization in a well known form. Let us do that. So, what we are doing is we are considering these 3 terms, right, and we will try to write them up. So, we write a function f of u, which is of this form u transpose a u plus z transpose u plus u transpose z, where of course, let us see what are these. So, if you see u transpose a u, by that we mean this term, and then you have z transpose u, that is the second one, and u transpose z is this last term, right. So, that would really mean something like this, right. Let me show. So, this is done, right. We do not need to bother about this because this does not have u, but what we have effectively done here is we have considered this as u transpose a u. So, this is my a, right, and this is my z transpose u, right. So, z, let us see what z is. Z is practically this, sorry, this is my, let us see. Yeah. So, A is this W plus gamma transpose S and gamma, and Z is this is U transpose Z, right. So, U times Z. So, essentially Z is this your phi transpose S n phi sorry gamma transpose S n phi xn minus 1. So that's your z, right? So if that's your z, then you take the transpose of that, you see that it's adding up, right? So this thing, if I assume this to be z, if I take z transpose, that's naturally coming as, right, so xn minus 1 transpose, then phi getting transposed. Sn is like assumed to be a symmetric one by its form, like the way we have taken it, right? So Sn is fine, and then you have gamma transpose, again a transpose, so that becomes gamma. So that's z transpose here, right? So this is what you have, right? So now let's do some modifications here. So what we can do is u I just rewrote the same thing, but along with that I will just add and subtract one term. Question is why? The reason I do this is because as it seems that now I can take these 4 terms together, apart from these 4 terms, and I can again create a nice looking quadratic form. So that's what I see, right? Now since this is a quadratic term, right, this is non-negative, right? So that only means that, well, this function fu can be minimal with a value which is equal to this. So fu min would be this, and this will happen when this u is equal to minus A inverse z. Okay. So what does this mean? Now we can write that, well, what does this mean? U is un minus 1, and what is A inverse? So this is my A, right? So wu plus gamma transpose Sn gamma. So fine, that's my A, right? So inverse of that times z, right? So what is z? So this is my definition of z here, right? So if I take it up, gamma Sn phi. So in fact I don't need this bracket also here. Yeah. So this is what we get, and fine, we can write this as some function g of n minus 1. Which one are we writing? Well, this much, right? This much is g n minus 1, okay, and that gets multiplied by x minus 1. So you see, here is your control, right? So just like we are habituated to a form like u equal to minus kx, you have un minus 1 equal to minus something times un minus 1, and we are in keeping with the step n minus 1, we are writing it as n minus 1 of g, the n minus 1th step value of the gain, and the gain value comes up to be this based on our definition here, right. So, this is my gain matrix then. So, as we can see, this method tells me that this function will be minimized, because that minimization of the function is our objective, right. And if I minimize this function, it is a loss function, because it tells me that then the energy of the system is minimized with minimum value of x almost near to the stable state and minimum expense of energy for control, right. So, what I have is Gn minus 1 equals it is a long derivation, but that is just for your understanding. Of course, I am not going to ask you to do this derivation as part of an exam question, but you want to understand how a typical quadratic problem is solved. This is a classic example. So, that is why we are actually taking the pain of moving through all these optimizations involved in solving this quadratic program. So, that is it. Gn minus 1 is given by gamma u, wu plus gamma transpose Sn gamma whole inverse gamma transpose Sn phi. So, that is your n minus 1th step gain, and you have a definitive way to calculate it given the parameters of the system. Do I have all the parameters? Well, if you inspect, you have Sn, right, but Sn is defined as q naught, right. So, that is not a problem. But the question is, that is only the n minus 1th step. Now, do I have to obtain expressions for all these steps? How do I really go about it? So, let us figure that out. So, what we will do is, now we will use this result in the original definition of V a, Vn minus 1 that we were writing, and let us see how, where does it take us. So, fine, maybe we end this lecture here, and we have already consumed my time, right. And so, maybe we will start from right here in the next lecture. Thank you.